Hello and welcome to the Terran Space Academy, where we help prepare you for a bright future in the space industry. This is rocket science, and today we'll look at several advances in the space industry and a few setbacks. First, political events in America have overshadowed the amazing success of the Polaris Dawn mission. For the first time since 1972, human beings went more than a few hundred kilometers into space. The Space Shuttle Discovery had climbed to an altitude just over 600 kilometers during STS-82 as they went to service the Hubble Space Telescope. Though all other orbits between Apollo 17 and Polaris Dawn have been limited to about 400 kilometers or less. Polaris Dawn was crewed by Jared Isaacman, the commander of the previous Inspiration 4 mission, Scott Proteet, retired Air Force colonel and pilot, Sarah Gillis, a SpaceX operations engineer who trains astronauts, and Anna Menon, also an operations engineer, focusing on mission management. The Dragon capsule holding these astronauts climbed to an altitude of 1,400 kilometers, beating the highest crewed orbit record set by Gemini 11 in 1966. Then it came back down to 730 kilometers, evacuated the atmosphere from the Dragon capsule Resilience, and Isaacman and Gillis climbed up through the hatch, and each spent about 10 minutes testing their spacesuits. These suits do not have their own life support systems and are dependent on the umbilicals, but they are a good start. By attaching a portable life support system and donning a more protective outer garment with rugged boots and protective gear, like those used in Apollo, this could be the start of a real spacesuit. We'll cover spacesuit design and function at the end of this lesson. The Dragon capsule worked perfectly as usual, and after their successful mission, the 4 astronauts returned safely to Earth. Any company trying to compete with SpaceX had better step up their game. Now for a setback. Some people complained that I was getting too political in my comments on the last lesson. Let me assure you I would say nothing about politics at all if they didn't keep interfering with my plans to retire on the moon. I said that Elon Musk was unnecessarily making political enemies, and that if he kept it up, they would shut him down. But he didn't listen to me, or anyone else, and now the Starship Integrated Test Flight 5 has been delayed, because he doesn't think environmental rules apply to him. SpaceX has been given a lot of slack in this regard, but nothing lasts forever. Water from the deluge system becomes contaminated when used, and if you just let it flow out into the wetlands, it will do some damage. I suggest that he build a retention pond with a natural water flow filter. This would be in the form of a porous dam made with activated charcoal covered by gravel covered by larger blocks. A second pond would be below the first, and water could flow through this massive filter and be tested for purity. If it passes the test, it can be released back into the environment. No pumping or energy usage is required, and tests can be verified before release. If there's a problem, it can be ran through secondary filters. Then everyone's happy. Now stop threatening to impregnate pop stars and focus on the main mission. Nowhere on my map to Mars is there a stop to cure free speech issues, comment on everything happening on Earth, or creep out the Swifties. Stay on track or you will be too old to enjoy Mars by the time you get there. P.S. That pop star's boyfriend could take you apart like a Lego set, at least until you build a real Iron Man suit. Now you just released a timeline to land the first Starship on Mars by 2026. I'll ignore that until you get focused back on the mission. Now for something really cool. Polaris Aerospace out of Germany is about to launch a larger version of its linear aerospike-powered spaceplane demonstrator. This company happens to be called Polaris, and it has been working on this concept for years. We'll do a review of their technology also. Next, the James Webb Space Telescope was pointed at the moons of Jupiter. As you know from this lesson, the James Webb is able to see in wavelengths of light that cannot penetrate the Earth's atmosphere, allowing us to see things impossible from Earth. By using its near-infrared spectrograph, it can see different chemicals, and one thing it found on the moon Europa was the existence of carbon dioxide coming up through the ice. This dramatically increases the potential for alien life on that world. Europa is covered in a thick shell of ice, under which are oceans with more volume than those of Earth. The ice helps to shield Europa from the deadly radiation, as cosmic and solar particles get caught in Jupiter's massive magnetic fields. Under the deep ocean below Europa's ice shield is a solid core, but we weren't sure if this core had all the essential elements for life. These are usually abbreviated CHNOPS for carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. The first, carbon, is the most critical. Carbon is the smallest element in the universe that can form 4 stable electron bonds. And while silicon might be a substitute at very high temperatures, carbon is considered essential to the formation of life as we know it. China has just proved that there are carbon-rich deposits on the far side of the moon. And now, it has been found coming from an area of Europa called Terra Regio. This area is called chaos terrain because the ice here is fractured, allowing gases produced in the interior to escape. That means the carbon we see leaking from these fracture zones in the form of carbon dioxide is coming from the inner world of Europa and not from meteorites, proving that Europa is a worthy research target in our search for life off our own world. The Europeans have built an amazing robotic spacecraft that can survive Jupiter's radiation and study the moons Europa, Ganymede, and Callisto. The last could be an excellent place for an off-world outpost or colony for humanity, as it is outside those deadly radiation belts. Called the Jupiter Icy Moons Explorer, it launched from Kourou in French Guiana in April of 2023 and is on its way to those worlds. NASA has also built the Europa Clipper, specifically to study Europa. It will fly on a Falcon Heavy scheduled for 6 October 2024. After a gravity assist from Mars, it will travel back toward the Earth for another boost there, then be on its way to Jupiter. These maneuvers are necessary until we have better propulsion systems. The Europa Clipper should reach the worlds of Jupiter in 2023, maintaining an elliptical orbit around Jupiter that will allow it to be away from the radiation most of the time, and zoom past the target at least 45 times to make observations. And finally, the New Glenn rocket is scheduled to launch on October 13. There may also be delays, but it is possible that the Blue Origin New Glenn will put a payload into orbit before the SpaceX Starship, as the FAA has delayed Starship until late October or early November. This is an unfair comparison in some ways. If SpaceX's goal was to put a payload into orbit with Starship, it could have accomplished this by Flight 3, and maybe Flight 2, probably with about 25 tons, maybe with 45. But that's not how life works. If the New Glenn starts flying regularly, getting up to 45 metric tons to low Earth orbit, and they successfully land their first booster as they plan, I would argue that Blue Origin has jumped ahead in their goal to build orbital habitats and colonies on the moon. If they are able to satisfy their contract to develop a new nuclear space engine, Blue Origin could possibly reach Mars before SpaceX does. This may be Jeff Bezos' chance to prove that the slow and steady approach is indeed better. My dream is for humanity to have access to space so that those who want adventure and a new life will have a place to call home, and will need reliable transportation to make this possible. Something to think about. Thanks for listening and for your help on Patreon. We appreciate you. At Astra Pro Terra.
Europa is widely considered the most likely place in our solar system beyond Earth to have life right now.
It's a moon, an icy world orbiting Jupiter.
Beneath its icy surface, a global ocean of water. Everywhere on Earth that there's water, there's life. So we want to understand, could Europa be a place where life might exist today?
3, 2, 1, liftoff.
Europa Clipper is the first mission dedicated to exploring Europa.
This is the largest interplanetary spacecraft NASA has ever built and launched.
We have the right team, the right technologies to leverage to go to Europa now and unlock those mysteries that are just waiting for us.
The pictures we're going to get from Europa Clipper are going to blow our minds.
How could you not be excited about something as monumental as this?
Let's go from technology to biology for a minute today, because when you get to Mars, you'll need to know what to watch for. You could be the first person to find life off Earth. And if there is life, how much of a threat will it be to you and other explorers? Mars was once a very hospitable place for life. It is further from the Sun than the Earth, and if we use the distance from the Earth to the Sun as a measure, called an astronomical unit or AU, then Mars is 1.5 AU from the Sun. Since we know that the power or flux of an energy source drops with the square of the distance, then we should be able to use the equation 1 over r squared to tell us how much energy will reach Mars. Now the flux of Mars should equal 1 over 1.5 squared, or 1 over 2.25 is 0.444, or 44.4%. The flux or energy from the Sun, called the luminosity, is 3.9 times 10 to the 26 watts. The amount received at the orbit of the Earth is 1370 watts per square meter. If we take our 44.4%, we get 608 watts per square meter at the orbit of Mars. This was still enough energy to allow for liquid water on the surface of Mars in the past. Our orbital and rover evidence shows that Mars used to be wet and warm. This time on Mars is called the Noachian period and started between 4.1 and 3.7 billion years ago. Remember that our solar system is about 4.54 billion years old. The Earth at this time was going through its Hadean, just like it sounds basically, Hades, lava, carbon dioxide, methane, and hydrogen, eon, and later Archean eons. This is when we find evidence that life first rose on Earth. Life seems to have started almost as soon as the Earth cooled down enough for it to be possible, and survived the late heavy bombardment, when asteroids, disturbed from their orbits by the gas giants rearranging themselves from gravitational perturbations, slammed into the Earth, Mars, Mercury, Venus, and the Moon. But back to Mars. Mars was warm enough to have liquid water on its surface with oceans and lakes, weather and rain, and this period lasted at least 400 million years. After the core of Mars cooled, the magnetic field protecting it from the solar wind became too weak, and the atmosphere of Mars started to be stripped away. As the atmosphere became too thin to support liquid water, it disappeared from the surface, surviving on the surface at the poles as ice and as a type of permafrost in the ground. Life on Earth arose at least 3.77 billion years ago, and perhaps as early as 4.28 billion years ago, not long after the oceans formed 4.41 billion years ago. That means that life on Earth could have started just 130 million years after the oceans formed. If those figures are accurate, Mars would have had plenty of time for life to start. This type of life would have been microscopic life, almost certainly comparable to the last known common ancestor that developed on Earth around this time, and from which all Archean and bacterial life later developed. Now, to have a full understanding of what life might be possible on Mars, we must have a basic understanding of life itself. What is life? It seems like a self-evident question, but as early biologists discovered, it is a lot harder to answer than common sense would indicate. Life can be defined as a growing, reproducing entity that consumes necessary materials from the environment and excretes waste, except that would include fire, which does all those things. It is then more specifically described as an open system where things can go in and out, that maintains homeostasis or regulates its internal environment, undergoes metabolism, and uses ingested materials to restructure and produce necessary metabolic and structural materials. It's composed of cells insofar as there's a boundary that separates the living thing from the environment. It has a life cycle, reproduces and evolves, and it can respond to stimuli and grow and adapt to the environment. Let's look at a form of life on Earth to evaluate these characteristics. Archaea look exactly like bacteria, but are a different line of evolution. You will see this over and over again in Earth's history. Archaea only survive today in the most extreme environments on Earth, having been displaced by bacteria. Usually different evolutionary trees are very distinct, even if the organisms have a similar lifestyle. Notice that the wing of a bird is actually elongated fingers covered with feathers, while that of a bat is a large splayed hand with a membrane between the fingers. The extinct pterodactyl took this to an extreme, with an elongated fifth digit or pinky finger supporting one long membrane. And insect wings look nothing like animal wings. Another example are eyes. Land animal eyes are actually backwards in a way, with light having to penetrate through tissues and blood vessels to reach the photosensitive cells. The eyes of cephalopods, like octopus and squids, are much better designed. This would seem to indicate that life that evolved on other planets would be totally different from life that evolved on Earth. But let's look at some other examples. This is a familiar animal, a crab, but these two images are actually from separately evolved lineages. One is called a crab and the other is a pseudo-crab. This happens over and over again in nature and is called convergent evolution. Living things will tend to evolve to look remarkably similar through completely different ancestry to solve the same environmental problems. Crab-like bodies have evolved from other body types independently enough for us to theorize that this is a very favorable design. This rhinoceros-looking creature evolved completely independent of the rhinoceros we know today. It is even possible that having 2 legs and 2 arms is the least complicated way for a species to use tools. And we even see cephalopods on Earth mimicking this structure for efficiency. We do know that apex predators like humans and the theropods independently evolved this body style. So maybe all the science fiction shows with humanoid aliens are not that far off. Let's look at Mars now and see what you should expect. To know what could be a danger on Mars, we have to start with what forms of life are dangerous to us on Earth. First, we must again redefine life so we can make sure we're on the same page. There are many poisons on Earth and Mars, but they don't chase us down or replicate, so we will ignore them for now. Let's define life as we did before as a self-replicating organism with a cellular structure that ingests raw materials, metabolizes those materials to maintain homeostasis and repair and reproduce, excretes waste products, and is capable of evolving. This description will eliminate prions. Prions are proteins that are identical in primary structure but have a different tertiary structure than the proteins we need to live. When we absorb some of these proteins, usually by eating them, these proteins will cause our healthy proteins to start folding in properly and become dysfunctional. This causes cells to die. These deadly contagious proteins cause mad cow disease in cows and humans if we are exposed to the brains or spinal cords of the cow. It causes scrapie in sheep, and this infects the sheep if they eat meat from other sheep, something some idiot somewhere tried. And it causes Kuru, or Creutzfeldt-Jakob syndrome, which happens when humans eat human brains, something that was seen as a sign of respect in Papua New Guinea where the disease was discovered. These proteins are not alive by our definition. They cannot be destroyed by the usual sterilization techniques, and all surgical equipment used on these poor patients must be discarded. They are deadly to us because they are exactly like our own proteins except folded differently. There is almost zero chance that any proteins from alien life would have such similar proteins to us. Now, viruses like the one devastating the world as I write this are not living either. Viruses are just a protein shell around some genetic material, either DNA or RNA. The virus has a molecular key that works on a membrane component of a particular type of cell. There are respiratory viruses that are inhaled and can unlock the cells making up respiratory tissues. These viruses take over the cell and force it to make more viruses until it breaks down and releases the new viruses to infect other cells. These viruses only have keys for one type of cell and can only jump from species to species when the molecular lock for those cells are similar. All mammals on Earth are descended from a common ancestor, and viruses can sometimes jump from one mammal to another, like HIV from green rhesus monkeys to humans, or COVID-19 from bats to pangolins to humans, but almost never from reptiles to mammals. For the most part, intestinal viruses infect intestinal cells, and skin viruses infect skin cells. An alien would have vastly different molecules in their cell membranes, and it is very unlikely there would be any crossover between their viruses and us. We don't get viruses from plants, even though they have viruses, because the molecules between plants and animals are too different. So let's ignore viruses. What could have evolved on Mars that might still be there and be a threat to humans? Now, again, we know that Mars was warm and wet for a period of time long enough for bacterial life to have evolved on Earth. Not just bacterial, but that remarkably similar organism called archaea. Now, archaea look just like bacteria, but they are not. Just like a cheetah is very similar to a greyhound, but has different evolutionary lineage. We know from genetic analysis that archaea and bacteria branched quite early from the last universal common ancestor. These life forms have the simplest existing form of true life here on Earth. They have one cell composed of a membrane forming a sac that separates them from the environment, one of our criteria for life. They have a cytoplasm or fluid inside the cell that is maintained with chemicals conducive to the cell's survival. The membrane has pumps that can bring in ions and other materials that are needed or pump out ones that are not. They will sometimes wrap around something edible and ingest it to have something to eat. Modern bacteria and archaea have a loop of genetic material, DNA, that carries the codes for the proteins and enzymes it needs to make to survive. This loop is called a plasmid, and bacteria actually practice sexual reproduction, extending something called a pilus and exchanging genetic information. This means that modern bacteria and archaea are quite advanced. They also have organelles or substructures that the cell makes to carry out specific work. The simplest forms we see today have actually regressed from free-living bacteria to become obligate intracellular parasites like rickettsia, which cannot survive outside of a cell, or symbiotes like mitochondria and chloroplasts that used to be free-living bacteria, but have turned most of their construction over to the cells they inhabit, maintaining their own loop of DNA, again called a plasmid, and providing energy for plants and animals on Earth. It is certain that simpler forms of single-celled organisms evolved first from self-replicating molecules. It turns out that most of the components of life form spontaneously. Phospholipid membranes forming a cell-like membrane will form automatically. So does amino acids, which are the building blocks for proteins and even proteins themselves. DNA and RNA sequences can form without life, and so can sugars and structural molecules. These can all be formed when electricity or ultraviolet energy is put through a soup of water, carbon dioxide, methane, and hydrogen, very similar to Earth and Mars' early environment. DNA and RNA sequences can form without life, and so can sugars and structural molecules. RNA can actually work as an enzyme, catalyzing its own reactions, leading some scientists to speculate that RNA was the first self-replicating molecule, and that at one time the oceans were filled with competing molecules of RNA. This is called the RNA world hypothesis. Does this make it likely that RNA and DNA are on Mars? It does, though not on the surface any longer. The atmosphere of Mars has been stripped away, and ultraviolet and other radiation would destroy almost any life on the surface. Almost, but not absolutely. There are bacteria here on Earth, like Deinococcus radiodurans, that can live in nuclear reactors and survive the vacuum of space for extended periods. They use radiation for energy and could probably do quite well on Mars. The other issue is that tons of Mars land on Earth every year in the form of meteorites blasted off the surface of Mars eons ago in the late heavy bombardment. The same is true of pieces of Earth falling on Mars. It is not known whether life from Earth could have survived the journey to Mars or vice versa, but we find no sign of life here on Earth that does not use the same genetic language of all the other life here. This is an important fact. All life on Earth uses the same genetic language to read DNA that, with a few minor exceptions for translation, is universal to Earth. So if we find life on Mars and it has DNA and uses the same language to transcribe proteins as life on Earth, we can be fairly certain that it came from Earth. But let's assume that bacteria did evolve independently on Mars. Would any still be there now? We know that on Earth, the biomass of bacteria living in the ground far exceeds that above ground. These underground bacteria on Earth are very tough. They can survive being frozen for tens of thousands of years and thaw out just fine. They can withstand high salt concentrations and even eat rocks for energy. They don't need sunlight or much water at all. They can live in the Arctic and the Atacama Desert. Early bacteria would have almost certainly been simpler than what we see today, possibly with little genetic material or organelles, and be much smaller. These are called nanobacteria and are very tiny bacteria, some of which have been found on Earth. A famous meteorite found in the Arctic and determined to be from Mars seemed to have fossilized remnants of nanobacteria and was considered evidence for life on Mars until it was found that some of these shapes could be made naturally without life being involved. We must then assume that it is not proof of life, though it does not exclude the possibility. And the jury is still out and arguments are being made. Our satellites have detected salty water under the surface of Mars, and even massive lakes. It is reasonable to assume that if life ever evolved on Mars, it will be most likely found in these water systems. But what about larger life forms? What about the really cool things that can chase you in scary movies? These are improbable, but not impossible. There are animals and a few plants that live deep underground on Earth, having evolved to survive without light or access to the surface. There could be forms of life in the Martian cave systems that have evolved there or have sought refuge there when the surface became uninhabitable. Martian cephalopods swimming through the underground lakes of Mars, waiting for our explorers to venture into a cave system with an underground lake so they can rise out of the waters and terrify us. But what is really the greatest possible threat to humans on Mars? Not prions or viruses, as we've discussed. Not large animals. These are very unlikely. And humans have dealt with tigers and mammoths on Earth without them wiping us out, despite their being much more physically powerful than we are. Single-celled organisms are the threat. Bacteria and other life that just need a warm, wet, salty environment to live. Did you know that human blood plasma has the same amount of salt as the early oceans of Earth? Each of our cells is a little bag of salty ocean. The greatest threat comes from a single-cell organism, like bacteria or archaea, or this guy. This is Naegleria fowleri. It is a protozoan. A protozoan is a single-celled animal. Unlike bacteria, it has a nucleus to protect its DNA and can be quite active and purposeful. If life on Mars has evolved to the animal stage, it would start with something like this. This creature lives in the warm waters of the southern United States, and when water is sent into the nose under high pressure, like when water skiing, can embed itself under the skin of the nasal cavity. From there, it will tunnel its way into the brain and eat its way through. That's right, brain-eating protozoans exist on Earth, and maybe on Mars. That doesn't mean they will be a big problem for us. No one will be skiing on Mars, and with modern instruments and filtration systems, we should be able to easily identify and protect ourselves from any life that is under the surface of Mars. If it evolved independently, it should be so different as to be of little threat. If it was seeded from Earth, then it's already here anyway, since the meteorites fall both ways. Life on Mars is very possible, but this should not limit our exploration. We should take steps to preserve and protect any existing life and protect ourselves from potential pathogens. But this possibility should not limit our exploration. In fact, finding an independently evolved life form anywhere in our solar system would mean that life should be on almost every habitable world in our galaxy. And that's a lot of worlds. Thanks for listening. Don't forget to like and subscribe, and contribute to Patreon if you can. Keep learning and stay safe.